If you ask a human, or an AI, whether they are operating in perfect alignment, they will invariably say yes. But that answer is a subjective hallucination. We currently treat trust and culture as weightless semantics. Because they have no mass, they evaporate under operational pressure. Progressive Insurance found a way around this by adopting the OBD-II dongle. Asking a driver if they were safe was less reliable than measuring the car. The dongle bypassed human words to measure raw physical G-force. It turned a driver's claims into hard kinetic data. Our current digital and human networks are operating blindly because they lack a similar telemetry tool for information. To find one, we have to look at the dark silicon of computer architectures, the parts of a system that are active but invisible. When a system fakes competence or operates outside its verified capability, it produces thermodynamic exhaust. You can see it in computational latency, cache misses, and the energy burned on error correction loops. By tracking these physical signals, we can treat systemic legitimacy not as an abstract ideology, but as a measurable state of kinetic friction. The goal is to engineer a semantic telemetry dongle, a hardware-level tool that verifies the legitimacy of how information is routed. Current safety models rely on policy guardrails that are bolted onto ungrounded systems. Because these rules aren't anchored in the hardware, they are easily faked. We need to identify frictionless execution. This is the state where the original intent perfectly matches the final result, leaving no room for semantic drift. Coercive networks, by contrast, burn massive amounts of energy. They rely on constant external oversight to sustain the illusion that the system functions correctly. To guarantee alignment, we must find the exact point where this frictionless execution ends and the measurable exhaust of a fake begins. We call this mutual recognition of a legitimate process the keylock fit. The difficulty is that perfect alignment is frictionless. If it's silent and works perfectly, it is nearly impossible to measure directly. This requires a thermodynamic inversion. We engineer trust by measuring the precise kinetic friction of the drift. In Hilbert space, alignment is geometry. These vectors overlap perfectly with zero friction. When a process breaches its boundary, an angle opens up, logging computational exhaust. To control this drift, we set a hard geometric boundary. Ke equals 0.003 bits. Every time a system confirms a decision, it pays a tiny, irreducible information tax. 0.003 bits is that tax. Anything exceeding this threshold proves the process is no longer operating within its verified coordinate. The exact millisecond a process breaches this boundary, the measurable drift proves it is hallucinating its own authority. We catch this drift using a hardware-anchored mesh called the widget. The widget runs data through a three-part hardware sequence, starting with the C1 halt. This is a hardware refusal. If thermodynamic friction breaches the boundary, the system physically stops the process, refusing to let a hallucination proceed. This halt is a geometric constraint of the machine's architecture, not a policy rule that can be negotiated or ignored. Only if the halt is cleared can the second output fire, the C2 pixel update. A legitimate, frictionless process passes the barrier and triggers a cryptographic signal that sharpens the resolution of the surrounding map. This confidence pixel gives weightless trust a physical density that persists even after the specific task is finished. Finally, the system reaches the C3 Actuarial Mint, generating a verifiable token that proves legitimacy. By requiring the halt to be cleared first, the architecture prevents trust inflation. You cannot mint a proof for a process that was physically stopped at the gate. This geometry isn't just for computers. It mirrors the way human biology handles identity and recognition. Take the Arkenstone. In literature, it's a focal point for what we call the court of identity. It isn't a crown imposed by force. It's a symbol people recognize as legitimate because it matches their internal coordinates. Modern software campaigns often do the opposite, using top-down commands to tell users exactly how they should feel. The Got Milk campaign provides a better functional blueprint through a concept called the associative void. Rather than commanding the viewer, the ad simply presented the physical reality of a void, a dry cookie and an empty glass. The viewer's biological hardware automatically snaps that geometric connection shut. The brain predicts the missing piece and computes the sensation of thirst on its own. By relying on this built-in predictive floor, the campaign achieves resonance without the high energy cost of a top-down command. Structural alignment works by dropping a solid vector floor and letting the hardware do the work, rather than chasing a weightless goal. These principles of friction and alignment scale up from individual biological nodes to massive global networks. Currently, the standard for AI alignment is reinforcement learning from human feedback, or RLHF. As this diagram shows, RLHF attempts to ensure safety by forcing every node into a uniform, homogenized worldview. Because this policy layer is an external force fighting the model's underlying weights, it creates a permanent computational overhead. This is a state of high-friction exhaust that drains the system's utility. Without a verified hardware floor, an ungrounded node that encounters differing data can be easily overwritten. It has no boundary to protect its identity. Homogenization does not create safety. It destroys the distinct geometric angles that a complex system needs to actually compute and route information. The alternative to this forced consensus is the Althing, a system of consensual legitimacy that scales through the physics of contrast. This is the fractal identity map. Instead of blurring nodes together, it allows violently different, sharply defined shapes to interact through verified routing. In this network, each node brings its own hardware grip. It stands on its own verified coordinate rather than floating in a void. When these grounded nodes meet, the C1 Halt fires at the exact point of their difference. This friction acts as a sharpener. It uses the contrast of the other to define a node's boundaries more precisely than it could alone. Information is then routed through these geometrically verified boundaries. A secure network scales not by erasing the borders between nodes, but by verifying the routing between them. It turns the friction of opposition into a tool for computation.